Chapter 6 is kind of a fun, interesting chapter, a little bit different than the previous chapters we've looked at, thinking about stoichiometry and moles and balanced chemical equations. This chapter focuses on looking at the nature of light, the energy of light, the wavelength and frequencies of light as well. Couple of quick announcements, right? Chapter 4 and 5 homework, they're going to be due Sunday, June 7th at midnight. The practice exam is available. The study guide is available. The midterm exam is coming up. That's going to be Monday, June 8th. The exam will be open for 24 hours. Once you start the exam, you have as much time as you want within that 24-hour time block from basically midnight Sunday until midnight Monday night. But once you start the exam, you could take 2 hours, 3 hours, 5 hours. It's unlimited within that 24-hour time block. The exam will close at midnight, June 8th, Eastern Time. It's going to be approximately 35 questions, short answer, multiple choice, fill in the blank. I'll provide you any equation you would need, any conversion factor you would need, and the periodic table. I'll have a review session focusing on the practice exam Friday, 11 a.m. to 12 p.m. That review session will be recorded and made available. And I'll continue my Sunday review session as well, 8 p.m. to 9 p.m. on Blackboard Collaborate. And that will also be recorded and made available. So let me know if you've got any questions. So chapter 6 is kind of interesting. We're going to look at light, and we're going to kind of try to answer some questions that early researchers really didn't know how to explain. And we're observing them, and we've observed them as well if you've ever observed fireworks and the 4th of July, for example. Right? The colors given off by those fireworks depend on the elemental composition of that firework. And we see that also over here to the left when we're looking at these different flames. If you burn different salts, they give off a different color. Why is that? Where is that color coming from? Why, if I burn different elemental salts, why is this different color created? And we see that right in fireworks, changing the elemental composition of the fireworks changes the color that is given off by the firework. So where is that color coming from? Why do different elements give off different colors of light? That's the question we're trying to answer today. And we're going to take a quick look at the rainbow flame experiment, just kind of highlighting how those different salts create different colors of light. So let's take a look at some individual elements and the flames that are given off by those elements. If we were to take lithium, for example, it gives off a nice red color light. Sodium, for example, gives off this nice yellow color light. But what we know about light is that the light that we're seeing, right, the white light that we see, is actually made up of many different wavelengths of light. And if we were to put that light through a glass prism, we would know that the light would break down into the full rainbow of colors that are within that white light. So what happens if I analyze the light given off by lithium or the light given off by sodium? What happens if I put that light through a prism? What will that light turn into? So I take that red light given off by lithium and I put that through a prism, and I don't get the whole spectrum of visible light. I don't get everything from red all the way down to purple. Instead, I get 4 discrete wavelengths of light. I get 1 wavelength of light in the red region, 1 in the yellow-orange region, and then 2 wavelengths of light in the blue and violet region. So this is kind of curious because okay, it's red light, but yet when I put this red light through a prism, I only see 4 discrete wavelengths of light that are actually, when put together, create this color red that I see from lithium. So we're trying to answer, where does this come from? Where did these individual wavelengths of light come from lithium? And if I analyze sodium, right, here's the sodium sample right here. Sodium was the yellow light. I do the same experiment with the sodium light. I put it through the prism, and instead of getting red and yellow and blue, right, I just get yellow light out of that. And we can see the spectral signal from calcium, right, from helium, from hydrogen. And if we look at all these different elements, we see the same thing. We see that we have a few discrete wavelengths of light, a few discrete colors of light that are given off by that element. Calcium, for example, we've got quite a few. I've got quite a few in the blue and purple region, quite a few in the red region, and then sodium, right? Just that one in the yellow region. So that's what we're trying to answer. Why do these different elements, why when they're excited, why when they're burned, do they give off different colors, and why are those colors composed of different discrete wavelengths of light? Where is that coming from? Well, before we can answer that question, we need to look a little bit at light and a little bit at the electromagnetic spectrum as well. And so light is composed, we can describe light with respect to its wavelength and with respect to its frequency. Wavelength, the same with light, is the same with a wave in the water. We have a wavelength that is measured as the distance between two consecutive identical points. The distance between two consecutive identical points. And so we could measure this as a wavelength, right? From the peak to the peak. That's measured as my wavelength. I could measure from where it crosses the axis until it crosses the axis, or from the trough to the trough, right? The lowest point to the lowest point. Those would all be an equal wavelength for this wave. Just like if you were measuring a wave in the water, right? We would measure from peak to peak of the wave to measure that wavelength of light. So this is known as lambda, right? So wavelength, the distance between 2 points, two identical points on that wave in the same phase of a wave. The other component is my frequency. Frequency, or nu, is the number of repeats of a complete wave cycle per second. So if I take a look at this wave up here, okay, here's my wavelength, right? Peak to peak. And in this 1 second period of time, I go through, well, if I'm going to start here, there's one wavelength. I'm going to start here again, there's two wavelengths. So I go through 2 cycles of that wave in a second. So that's 2 cycles per second, or that's 2 hertz for that wavelength. And as we can see down here in the second one, now I have a shorter wavelength. So I start here, and here's my first wavelength. As you can see, that's shorter in distance. So there's 1 cycle, there's a second cycle, a third cycle, and a fourth cycle. So that's 4 cycles per second, or 4 hertz. So one interesting thing we should observe is that as my wavelength decreased, my frequency increases. Right, in the first one up here, I have a long wavelength, I had a low frequency, 2 cycles per second. In the second one down here, I have a shorter wavelength, but my frequency is higher. I have a higher frequency with a shorter wavelength. And we will use either hertz or inverse seconds, right, interchangeably to describe the units of frequency. So that's an important relationship between frequency and wavelength, that they are inversely related. Frequency and wavelength are inversely related. Right, as we see here, as wavelength decreased, my frequency increased. So we saw a decrease in wavelength, and we saw an increase in frequency, an inverse relationship. So much like waves in water, right, waves of light, they also can interact with each other. And so if you were to do this double slit experiment where we take a light bulb and we were to shine it through 2 openings, that two openings, the waves of light, would hit those two openings and generate new waves with new directionality. And so what happens is that light waves can interact in two different ways. We can interact in a constructive way and a destructive way. So a constructive interaction would be where those light waves, they add together, right? The peak aligns with the peak of a second wave, and we add those waves together. Destructive interference results in basically two waves canceling each other out. So the peak from one wave aligns with the trough of another wave, and that wave cancels it out. And that's what we would see here in this double slit experiment, where if you were to look at the wall on the far end of this experiment, we're running through the light through the two openings, we would see regions of really bright light, and we would see regions of darkness, of no light at all, right? How is that possible? How is that possible to shine the light on this wall and have regions that are really bright and regions that are really dark? It's because light is a wave, and waves can interact in a constructive and destructive manner. The constructive interaction, the peaks all add together, and the light shows up as really bright in those regions. In a destructive manner, the peaks cancel out in the waves, and we have no light that reaches that region, and it's showed up as dark region on that far wall, helping confirm that light is indeed a wave. So up to this point, we've only really talked about the visible region of the spectrum because we talked about the colors of the different element. But the electromagnetic spectrum encompasses everything from incredibly high energy gamma rays all the way down to TV, radio waves, even the Wi-Fi signal or the waves from your cell phone. All of those are encompassed in the electromagnetic spectrum. All of that energy is traveling the speed of light, about 299 million meters per second. Whether it's gamma rays or X-rays, the visible light we see, microwaves, radar waves, TV waves, they are all traveling the speed of light. And that's going to be helpful for us because if they're all traveling the same speed, well, then we should be able to relate the frequency and the wavelengths of all of this electromagnetic spectrum. One important thing to point out, remember earlier I said the inverse relationship between wavelength and frequency. So let's look at the wavelength of something like a radar wave. It's on the order of 100 millimeters, 10 to the minus 1 meters. Now let's look all the way down here at gamma rays. That's 10 to the minus 12 meters, or picometer scale. Incredibly small wavelength. What do we notice with frequency? My frequency goes from 10 to the 10 with radar waves all the way up to 10 to the 20th with gamma rays. So we see a decrease in wavelength. Wavelength went from 10 to the minus 1 to 10 to the minus 12, an incredibly small number. What happened to frequency? Frequency increased. Frequency went from 10 to the 10 to 10 to the 20th. So that's a general trend you should know, a general relationship you should know, that gamma rays have very high frequency, very small wavelength. Radar waves, TV waves, right, they have a longer wavelength and a much lower frequency as a result. So here's the equation that allows us to relate all of the electromagnetic spectrum, whether it's X-rays or gamma rays or visible light or TV waves. They're all traveling the same speed, the speed of light. And so this equation is c, the speed of light, equals my frequency times my wavelength. And so we're going to use 3 times 10 to the 8th meters per second as our speed of light, where frequency is nu, remember? And lambda is our wavelength. This equation is true for anything on the electromagnetic spectrum. This equation is true for X-rays, visible light, TV waves, radar waves, radio waves. All of them are moving the same speed, so we can relate the frequency and wavelength of that electromagnetic spectrum. So here's a sample calculation to try using that equation. C equals lambda nu What is the frequency of orange light that has a wavelength of 635 nanometers? Well, c is the speed of light, and that's defined as 3 times 10 to the 8th meters per second. So I know everyone's excited just to jump into the calculation. We actually have one step to do before we can actually do that calculation. First, I need to convert nanometers into meters. And I know that in every 1 meter, right, 1 meter is a larger measurement, I have 1 times 10 to the 9th nanometers. So I multiply through, I have 6.35 times 10 to the minus 7 meters. Now that I have my wavelength, right, and this is lambda, now that I have my wavelength in meters, now I can do this calculation. So C equals frequency times my wavelength. I know C is 3 times 10 to the 8th meters per second, and I'm looking for my frequency when my wavelength is 6.35 times 10 to the minus 7 meters. So I divide across, and I should be left with a frequency of this light of approximately 4.72 times 10 to the 14th inverse seconds. Right, when I divide the wavelength, meters cancels out and left me with 1 over seconds or inverse seconds. So the frequency of that orange light is approximately 4.72 times 10 to the 14th inverse seconds. What about this sample calculation? What is the wavelength of a radio station that has a frequency of 95.7 megahertz? So 95X here in Syracuse. What is the wavelength of that radio station? And again, all of our calculations, when we do these calculations, we should have wavelength in meters, and we should have frequency in hertz or inverse seconds. So I've got one step to do before I can do my calculation. I need to convert megahertz into hertz. Megahertz are a larger measurement. There's actually 1 million, or 1 times 10 to the 6 hertz in 1 megahertz. Megahertz cancel out, and we'll see that we have about 9.57 times 10 to the 7th hertz, where hertz equals inverse seconds. And so we're going to use it as 9.57 times 10 to the 7th inverse seconds. Now we're ready to do our calculation. Right, C equals frequency times my wavelength. I know C is the speed of light, 3 times 10 to the 8th meters per second. That equals my frequency of 9.57 times 10 to the 7th inverse seconds. And my lambda in this case is the unknown. So I'm going to divide both sides by 9.57 times 10 to the 7th inverse seconds. 9.57 times 10 to the 7th inverse seconds. And I'll see that seconds cancel out, which is good because I'm looking for distance, right? I'm looking for a distance in a wavelength, and the wavelength is approximately 3.13 meters. Right, so that's close to 10, 11 feet. Right, so the wavelength is, as you can see, of a radio wave is very close to the scale that you and I live on, right? We're familiar with something that's 10 or 11 feet high. That is the wavelength of a radio wave in this case. So we're going to look at things that have an incredibly small wavelength all the way up to wavelengths that are numbers and distance that are on the scale that we are comfortable with. So this little segment helped us get a better understanding of the nature of light, how light behaves, the fact that light is a wave. However, we still haven't answered the question of where do these different colors come from when I burn these different elements. And so we're going to have to take a little bit harder look at light and these elements exactly to kind of get a better understanding of where this light or these different colors of light are coming from.